Okay, here are the problems on reflection and refraction of light. This question. You can see from the diagram that the person whose eyes are 1.64 meters above the floor stands away from a vertical plane mirror whose bottom edge is 38 centimeters above the floor, and you have to find the distance x. Okay. Now, when you look at this problem, you see that tan theta is 1.64 minus 0.38 by 2.30. How do you get that? Because tan theta, as you can see from the diagram that I've shown, this is tan theta, 1.64 minus 0.38, which is here, divided by theta. So this little triangle here, you can, as I've shown here, okay. So that gives you actually there's another formula for tan theta, which is 0.38 by x. So tan theta can be written in two ways, one from the bigger triangle and the other from the smaller triangle. So that's what you find here, 2, and they are put equal to each other. And we know that both those angles are theta because the angle of incidence is equal to the angle of reflection. And after that, it's just rearranging it to calculate x, which gives us 0.69 meter. And you are 88 centimeters from a plane mirror. What area of the mirror is used to reflect the rays entering one eye from a point on the tip of your nose if your pupil diameter is 4.5 millimeter? Here we are assuming that the eye and the nose are in the same vertical line. And clearly from the diagram, you see that the diameters on the mirror is represented there, the diameter of the pupil coming up there, but the angle subtended, the angle here is the same. So the angle can be written in two ways. It can be written as length of the arc divided by this radius, or length of this arc divided by this radius. Okay. So once again, angle is length of this arc. So d pupil divided by do plus di, or the same angle can be written as d of the mirror divided by di. Which is what I'm writing now. You're asked to find the area of the mirror, so if you get dm, now how is this half dp, because du is equal to di. Object distance equal to image distance, and area is pi r squared, or pi square of the diameter divided by 2, which is what is going on here. And simply substitute for dm as half dp, and that would give pi by 16 times 4.5 times 10 to the negative 3 whole squared, which when calculated gives 4 times 10 to the negative 6 meter squared. A dentist wants a small mirror that when 2 centimeters from a tooth will produce a 4 times upright image. What kind of mirror must be used, and what must its radius of curvature be? Definitely, because it's a magnified image, this has to be a concave mirror. And because it's upright, it has virtual. So it's a concave mirror producing a virtual image. DO 2 centimeters. Magnification is +4 because magnification is positive for a virtual image. Put it into the equation for magnification and you get a relation between DI and DO. -8 centimeter. Again, the negative shows that it's a virtual image. And then use the length equation from which we can find the focal length as the product divided by the sum. Put in all those numbers. Gives 2.67 centimeters. And the radius is twice the focal length. In this question, magnification of a convex mirror is plus 0.55 times for objects 3.2 meters from the mirror. What is the focal length? Well, positive magnification shows it's a virtual image and DO is given. So just like in the last problem, M is negative DI by DO, so DI is minus MDO. Substitute the values. It is 1.76, negative 1.76. Put into the law of distances. Focal length is product by sum. You have to be careful about DI being negative. It gives negative 3.9 meter. Here, a 4.5 centimeter tall object placed 26 centimeters in front of a spherical mirror. It is desired to produce a virtual image that's upright and 3.5 centimeters tall. It is a smaller virtual image, so it has to be a convex mirror. And to find the radius of curvature, use the formula for magnification, find DI, and then the length equation. That gives minus 90.55 centimeter. And then the radius is twice the focal length. Okay, on to the next one. Here the light beam strikes a 2 centimeter thick piece of plastic. Okay, you have to find the total distance, caps D in the figure. Now look at those two triangles that I've made. So first find this small distance from that triangle and then find this and add them up. That is the idea. For which you'll have to find theta 1 and theta 2 from the ideas of refraction. So that is Snell's law of refraction, which will help us find theta 1. and then applying the Snell's law at the second surface. So once you get theta 2 and theta 1, all you got to do is take the tangent in both those triangles. Okay, I'm trying to make it a little bit more clear. I hope you understood this. And in this one, the watchman shines a narrow beam of light, and you got to, it's a similar kind of problem as before. Once again, you have to find theta 1 and theta 2. Tan theta 1 is 2.5 by 1.3, as you can see clearly. And apply Snell's law. Find theta 2. And again use tan theta 2. So you've got to add the two distances now to get the total distance on the edge, which is 2.5 plus 1.895. Okay, now the figure should become much clearer, right? So what we found is this distance, and we had to add it to this to get the total distance. To find this distance, you have to find this angle using Snell's law. First we found theta 1, and then use that to find theta 2. In this question, you have an equilateral glass prism, and light is incident at 45 degrees. You have to find the angle at which light emerges. Okay, once again you have those four angles, theta 1, theta 2, theta 3, and theta 4. Let me show the whole thing because that was a mess up. Alright, so here you got to find theta 2 first here, and then use theta 2 plus theta 3 is A to find theta 3, and then use the Snell's law again at this point to find theta 4, which is what I've done. Pause the video and look at the picture of what has transpired. In this optical fiber, light reflects at an angle of 14.5 degrees. And you have to find the distance along the axis that the light travels between successive reflections. So once again here, you are asked to find x. If this angle is 14.5, this is definitely going to be 14.5, because if you draw the perpendicular here, these two angles will be equal. Therefore, these have to be equal too. So it's enough to take tan theta. You get d by x, and d is known, which is the diameter, and you get it. Now, in this question, the power of the lens is given. Remember that whenever the power of the lens is given, it is the reciprocal of the focal length in meters. So use that to find the focal length, and then use the lens equation to find DI. The negative there shows it's a virtual image. To find the height, use the two formulas for magnification, put them together, make HI the subject, and you have the answer. The positive shows it's a virtual image and it's upright. In this one, 105 millimeter focal length lens is used to focus an image on the film of a camera. Maximum distance allowed is given, and you have to find how far ahead of the film should the lens be. So actually we're going to find DI, because the image is formed on the film. Use the lens equation to find DI. DI is positive. Of course, it's a real image because it's formed on a film. And in B, same thing for 3 meters. C, same for 1 meter away. So it's just 3 different cases. But the D part says what is the closest object this lens could photograph. Now remember that when DO becomes minimum, DI becomes maximum. And DI maximum is 13.2 centimeters. Focal length is known, so 51.3. See, here it's a converging lens. That means it's a convex lens. Focal length is positive, and you have to find DO, object distance, to produce a real image which is the same size as the object. Now real image magnification is negative. Same size means magnification is -1. So basically DI and DO are equal here. And then put it into the lens equation. I'm going to show you how we get DI is equal to DO. That's the formula for magnification. But magnification is -1. And so you get DI is equal to DO, from which we get DO as 50 centimeters. A similar kind of problem here. Again, we have to find DO, but in 2 different cases. First, it's a real image, and therefore DI must be positive. Magnification must be negative. Now from the formula for magnification, we can find DI in terms of DO, and then put it into the lens equation. Now how many times have we done this? And calculate the focal length in terms of DO. Therefore DO is 70 millimeters. In the B part, same thing, but the image is virtual, means it's positive. And just notice that I was taking the magnification as 2.5 while the problem says it's 2. I am so sorry for that, but I hope you understood the idea in the problem. See, I just noticed it's 2 here. and I was using 2.5. Okay, here the object is 100 and how much is this? 1.30 meter away. Focal length is 135 millimeter. You got to find DI. And to find the magnification, use the two formulas. Make HI the subject. And in the B part, it says, what if the focal length was negative 135? That's in millimeter, that's why it's 0.135. Remember that. Well, in that case, let's see what we get HI as. .263 meter. Okay, the first case it's a real image, and in the second case it's a virtual image. Alright, thank you.